So we don't have the first speaker, so we need to see the line. If he doesn't show up for a long time, then we will just adjust the schedule. If each of us speaks for 5 minutes and there are no questions, then we will finish in 45 minutes. Well, everyone, thank you for joining. We are just waiting for the first speaker. Do you hear the audio signal?
Dr. Clean,
Yes.
we turned the quizzes today. We haven't done.
Oh, yes. But they're at the end.
When I leave early, just put it there.
But if you enable sound, do you hear it? With the audio connection work? Test.
Speaker is not working. Why is the speaker not working?
are the important people without whom we cannot start. Updated slides, not in the night version. So one way. London is in your version. Is there any substantial differences or it is cosmetic?
Like titles and some text and stuff. Basically, I put like some degree of context on the equation, so it's not just straight copy pasted.
Let's try to convert it to PowerPoint. Right now, there is no time, but you just go copy paste this image.
I don't have a computer that has PowerPoint.
Not today, before the next presentation.
Oh, okay.
Okay.
Are we doing 2 sessions?
But there will be finals and also presentations.
Okay.
And next time, just try to prepare PowerPoint.
Yeah.
Just quick to save. Oh, and we did not show it, but let me share screen right away so that we. Let's see. Even here is yours is upper right corner in the one updated photo in the also in the corner. If you need to find them. Here's mine, which is the easiest one. Thank you for continuing to support these meetings by your presence. So there are many important parts of the class that of the material in that cannot be fit into the lectures, and this presentation serve as accumulating credit as we should do in academic institutions, and from the goals of the course, they like you are heroes who cover the holes at the bottom of the ship so that it doesn't sink. So you cover missing part that we need to achieve to arrive to the glorious end. So here are the presentations, and I cannot say which one is more or less important. Everyone is important to achieve to the end. If even if we started like 10 minutes ago, if later, if there will be only 5 minutes and no questions, we will finish before 3. If we add 5 minutes of questions, we still will be in time. So questions are welcomed, and one of the standard question that one can ask even without thinking, like, what is the connection of your talk to the class material? And it will probably confuse the speaker, any speaker. So the materials are placed on the board of the screen. So those who were submitted during the night are here. And if there are some exceptions, they are in the top right corner. So come double click and start presenting. This thing has batteries. It's supposed to work, but it's more reliable to use keyboard and mouse if something doesn't work. So do not panic, just breathe, comment, and push the button. The first speaker, Adam Erk, is warmly invited to the stage. Not Erk, Flesche. I misspelled the name because 10 years ago I had another student with the same name but different last name. Yes.
Okay. Hey, you hear me? Okay. Okay. I'm going to be talking about the Jaynes-Cummings model for an atom in a cavity. This is a very general case. We can go to the next slide.
I'm not sure if I'll try, but
Oh, okay. Oh, you got it. Okay. So first, we want to define our Hamiltonian. So that's going to be constituent Hamiltonian. It's going to be made up of just a linear combination between the atom Hamiltonian, field Hamiltonian, and the atom field interaction Hamiltonian. This is going to be the most important part of today, but here's some definitions for the atom and field Hamiltonians. This is kind of based on an approximation that the Jaynes-Cummings model allows us to do. So we're only considering a two-level system. And so we don't have to sum over infinite wave vectors in this case. So we just have this, this sort of definition of the field Hamiltonian. Typically where was I going with that? I'll get to that later, I think. So in this definition of the atom field Hamiltonian, it's a bit ambitious again because it sums over all wave vectors. But we can work around this. We can set R to 0, and we can define our dipole operator as this raising and lowering operators. So we can simplify down to this term right here, where GC comes from how we simplify the term E, which is the electric field operator. We can go next slide. Oh yeah. Yeah, we really need to improve this. In fact, it would kind of help to get rid of that GC right now, but we're just going to kind of work through this together. We're going to remember from the interaction picture, our Hamiltonian is a combination of this 0 and 1. This 0 we can define as the atom and field and kind of forget about it for now. However, the interaction Hamiltonian, we're going to apply some time dependence and then end up with this wonderful expression here. And we're going to have to make some assumptions here. We're going to have to cut some corners. We're going to assume a very near resonance, or that mathematically the resonant frequency of the atomic transition and the resonant frequency of the cavity are about the same. This is to say this difference is about 0, and if you add them, it gives you about twice the cavity frequency. So with that, our anti-resonant, which is this case, will approach 0 because not approach zero, but they'll actually average out to zero in a very small time frame, because this is much faster in frequency than, of course, zero. So we end up with this expression. Now we just have these differences. These represent kind of detuning frequencies, but I'll get to kind of more of that soon here. We're left with this Hamiltonian, this definition of the Hamiltonian, just with this raising and lowering operator and the creation and annihilation operators that come with the cavity. We can go to the next slide. Yep, and now we're going to define the Jaynes-Cummings Hamiltonian, which is going to be a combination of these three things. Remember the definition of A and F, or HF, and then the definition that we just defined using the Schrodinger picture for the interaction Hamiltonian. So it's just this linear combination. We're going to neglect 0-point energy, which is this. So we're just left with this. We're getting rid of this. And we want to introduce another operator. It's called the number operator. It's going to commute with our interaction Hamiltonian, which allows us to kind of do some cool tricks and come up with a pretty cool matrix that I'm going to need to go to the next slide for. So this indexes all states up to n, or index to n, which can be photon count or the quanta count. And so with this next slide, I'll just kind of talk about this.
Commuting with Hamiltonian, what does it mean? If an operator commutes with Hamiltonian, which property corresponds to this observable?
The states defined by n are states of the Hamiltonian.
If an operator does commute with Hamiltonian, it doesn't change over time, right?
Yeah.
Okay.
This is stationary.
Yeah. Please keep going.
Okay. So yeah, we just have this. I have another picture on the next page, kind of saying more about this. But we're just left with this big matrix, and each HN can be given by this 2x2 square matrix. So this is in the eigenstates of n, which I think are what do you call them? It's in it involves the tensor products between each n and transitions between ground and excited states. But we're going to do better, make this approximation here, or not approximation. We're gonna say that this product here equals again our GC, which is the dipole matrix element. And then we have this square root n term, which I'll kind of visually show how that manifests. So maybe we can call 2GC the Rabi frequency instead of having it just stick around forever. And then maybe we can call this the detuning frequency, as I kind of mentioned earlier, delta. We know how to work with these two things. We've done it before. And so this is the simplified matrix. This is actually shifted by a factor of 1/2 h bar delta from the excited to ground state. So this is the 2x2 matrix representing this nth Hamiltonian for us. We can go next slide. Okay, we diagonalize, and from that, of course, we can get the eigenenergies and eigenvalues and eigenstates, I guess. So we're left with these two latter terms. These allow us to predict or go up a step of n to describe the energy of the next state, of course. Here, tan theta n, this angle, is defined by this term right here. So now we have these ladder operators, and now, of course, we have definition of our eigenvalues. We can go to the next slide. Okay. The energy gap between those states are going to be equal to this. In the resonant case, or the very near resonant case, we're of course assuming that delta is 0 because this difference is close to 0. They're the same. And so in that case, the latter term simplifies to this, and the energy gap is defined by this. We have a factor of the square root of n, where the energy difference is going to be scaling with that. So on the next slide, we have a visual sort of representation of that. Yeah. So because it's the square root of n, of course, this splitting is going to be nonlinear as you climb. Just an example, you have square root 2, square root 3, of course, all the way up to square root n. So this is sort of central to what we've been learning in class with respect to NMR and stuff. So yeah, I think that's it. Is there another slide?
Questions?
Like 2 slides back,
Okay.
you'd find the tangent of theta n. Why do you need that? It doesn't look like it shows up anywhere.
Well, if we want it in terms of our Rabi frequency, that's all we really need it for.
Yeah. Well, because then, like, if you were to use that, then it becomes problematic if you are in resonance, because then delta is 0, right?
Let me contribute. For delta equals 0, arctan of this in infinity will be 45, and it will be 50-50 mixture, like 1 of square root of 2, 1 of square root of 2.
Okay.
And if one is away from resonance, the relative deviation is proportional.
Okay.
Yep.
So sorry for.
Slide. Wondering the G, is your G, does it represent coupling, and why does it have a conjugate?
G represent coupling. You're talking about GC?
Yeah, like why is there like conjugate of it?
Where are you seeing a conjugate?
Like the stuff.
Oh, right here. That comes from when we do this, we just take the complex conjugate of it.
Or can you point with
This time dependence. You can represent each of these to these sort of operators. Does that make sense?
subscript C is probably for cavity.
Yeah.
Sub C for cavity.
It's the dipole matrix element for the cavity. So as I said, it kind of comes from us breaking down that the dipole form of the Hamiltonian. We use this term in front as kind of a leading term.
I have a question. How do you prove that your matrix of Hamiltonian has this block diagonal form? It's a really nice symmetric property, but is there a proof of this? Or intuitive understanding why it should be so simple and symmetric?
If it commutes to 0, it must, right?
Why Hamiltonian matrix is composed of these blocks of 2 by 2 matrices? Why not the whole Hamiltonian is populated with values?
With just values? Oh,
Why the most of the
yeah.
Hamiltonian are zeros?
So in the harmonic oscillator, you have an infinite number of states, but we've coupled this to a 2-level system, and so that's what we're using to describe these diagonal elements. We're describing a 2-level system, or infinite number of 2-level systems.
I would expect something like, if it is in resonance in 2-level system, it allows only one step up or one step down. Therefore, if there would be a possibility to jump 3 or 10 states down or above, the whole Hamiltonian will be non-zero. But this availability to jump only one step up or down makes most elements of Hamiltonian zeros.
Okay.
Okay. So it's just the availability only emit or absorb one quantum.
Yeah.
Okay. More questions? If no, please join in thanking Adam. His talk used 14 minutes. Just to let you know. So is it enough space to I'm taking the glorious role. If ever by the chance you find by the slide advancer, it would be great. If not, just let's edit.
So is this good for is this good for volume? All right. Okay. So I'll be presenting on the coherent states of an electromagnetic wave in a resonator. So if we can go to the next slide, please. All right, so some definitions, coherent states. We're going to denote it with this vector alpha. These are single mode states that are superposition of classic harmonic oscillator states labeled by N. And these coherent states come from classically oscillating electromagnetic fields. So while the word classic is getting thrown around a lot, we need to remember that these are still quantum states. They just happen to have some behaviors that are very classic-like in nature, which makes it useful. There's some various equation definitions that you can find in literature for what these coherent states are. Like I said, we have this superposition where, again, N is this harmonic oscillator state. You can define how a annihilation operator from the harmonic oscillator acts on it. So if this annihilation operator acts in coherent state, we're going to get the eigenvalue out. You can also define it in terms of something called a displacement vector, which refers to some sort of displacement of a vacuum. And in that case, then we get this definition down here with an exponential with creation and annihilation operators. So why is it called coherent? If you were to plot this coherent state in terms of position space, and then you propagate it in time, it has a minimum uncertainty wave packet because it is a quantum system. And as it moves throughout this harmonic oscillator potential, it's going to maintain its shape. It's not going to disperse over time. If you see like wave mechanics simulations, like you see waves disperse over time as they were spread out. And this doesn't happen in this case if you're in the position space. So how are we connecting this to the electromagnetic field? Because in class we deal with oscillating electromagnetic fields. We have our vector potential, and I presented on this a couple weeks ago, when you could put the vector potential in terms of creation and annihilation operators. If you have this electromagnetic vector potential, you can calculate an interaction energy in terms of this current and vector potential, and you can put this into a propagator. And since the interaction energy has a time dependence, you need to make some approximations with the propagator. So if you were to do some infinitesimal time step, you could get our interaction energy here, which still has this vector potential, and then you do some more mathematical steps and you can get the dynamics or the propagator of your system in terms of a phase factor and this displacement operator, which has this coherent state eigenvalue in terms of some time interval t. So if you were to take the expectation value of the electric field in terms of these coherent states, you would recover something like the classic oscillating electromagnetic wave behavior, just with some quantum fluctuations. So we have like this thicker line here. So again, we have something close to the classic behavior with some quantum flavor to it. So next. All right. In Adam's talk, he talked a little bit about this idea of quanta and our number operator, since we have this coherent state, which by the way, is like a single mode operator, or a single mode state, which fits into our idea for the Jaynes-Cummings model. It turns out that if we take the expectation value of the number operator in terms of our coherent states, which will give us the average photon number, quantum number definition, we already defined the action of a annihilation operator acting on this coherent state as its eigenvalue. So this gives us a nice interpretation that the eigenvalues of this coherent state can give us the average quantum number. We can calculate the uncertainty of the photon number since we're dealing with averages, and we can calculate the probability of detecting these coherent states, which, as it turns out, is a Poisson distribution mathematically. And if you were to plot this Poisson distribution for different averages, you can get different looking distributions. So here we have a smaller distribution, and then as the Poisson distribution grows with a greater number of things it's averaging over, it begins to look more like a Gaussian. So we get this Poisson behavior. Since we can vary the average number n, or you can vary your like eigenvalue alpha, it's a similar idea. You can get different behaviors for increasing n, or the way n and the eigenvalue alpha are related. And I try to look up an experimental example from literature. And I guess in an experiment, you get something like this for this particular example. They were looking at coherent state, and somehow they transferred this like probability and time thing into this Poisson distribution. So they were able to recover this expected like Poisson distribution for how the average quantum number are expected to behave for a coherent state. So I guess that's my presentation. I'll leave it open to questions.
Right, Jen, thank you. 6 minutes for the talk. Questions are, presentations open for questions. I do have one. With your permission, I'm going to slide 6 and want to ask you, how did you derive, or if you just borrowed it from the textbook, how to find that the deviation of number of quanta is square root of n? Like if you need to derive it yourself, what would be the strategy?
I think I'd take the definitions of n squared and n, and then I would just mathematically work it out.
And why they're not, why this subtraction will be not equal? It is right direction of thinking. You can just tell by words what is next, just to save time.
I guess you'll find that if you square this, you would just get some sort of.
So one needs to bring the product of operators to the normal ordering, right? So that everything with conjugation go first, everything without conjugation go second. So that it will be converted into a dagger, AA.
Yeah.
And then to make this, one would get additional terms, and they will be responsible for these two things not equal.
Yeah, so it's like Book's theorem kind of thing.
Exactly.
Yeah.
More questions? If no questions, let's thank Hadassah once again.
So before we start,
very interested in this presentation, and I want to convey productively what my thoughts are. So I hope you allow me to read out my thoughts alongside my presentation. So I'll do less of rambling, more of conveying what I really like about my presentation. So we're going to be discussing the interaction of a two-level system of an atom in which the ground state and the excited state is chosen for convenience with a single mode radiation, and explore the time evolution of the coupled system in a non-coherent state and a coherent state. And we are also going to explore the trajectory of the interacting system in a non-coherent state and in a coherent state. So here is the Jaynes-Cummings model Hamiltonian, which describes the interaction of the atom and the radiation. It happens to do a lot of things around the research. So in order to solve the time evolution of the system, it is convenient to switch the interactive pictures, which was discussed by Adam in the last presentation, where the Schrödinger state, which contains all the time evolution, is transferred into the interactive frame. Next. Therefore, the time evolution in the interacting frame is given by a Schrödinger equation for a state vector in the interacting by a state vector in the interacting picture, Schrödinger equation. And our interacting Hamiltonian, which has become time independent due to the transformation into the interacting picture. This. So these are the only change we observe between this and what I showed earlier is the inclusion of this exponential component into the interacting picture, and also the delta, which shows that, which conveys the tuning system. So to calculate the time evolution, we start from a general wave function in which it is expanded into this proposition of some basis vectors, in which the basis vector we choose was from the ground state with an error n+1 photon and an excited state with n photon, having complex coefficient of C1. When we solve for C1, a complex conjugates C1 and C2, here it's a very curious question to ask that which of the states are coupled in the interacting Hamiltonian. So the atom in the ground state is coupled to the atom in the ground state, to the n+1 photon is coupled to the atom, is coupled to the state, excited state with n+n photon, which is also called absorption, and vice versa. So we have like a process of excitation and emission in a two-level system. So far C1 and C2, we decided to use a series of differential equations to solve for the coefficients of the ground states and the excited state that was shown in the previous slide. I was too lazy to confirm that this is right, but I trust them because who am I? So this is, in a general sense, what it did was just by plugging the wave functions, which I showed in the last slide, into the Schrödinger equation, and it came out to the solution of this solution, which is the time derivative of the complex coefficients of the ground states and excited states. So let's take a look at the solution of the differential equation at different initial conditions. So the first initial condition I spoke about is when we have a atom in the ground state with n+1 photon at time 0, and and the system is in resonance. That means the tuning is zero. So we are able to get the solutions of the complex coefficients to be this. This shows that the complex coefficients, which also describes the amplitudes of the system, is in the form of sine and cosine movements, as seen here at different states, sine and cosine. So if we are to calculate the probability of the atom in different states of the atom in these initial conditions, we are able to get that the probability distribution, which is this, and doing so many trigonometric functions give this. So the probability distribution is the probability distribution of the atom being in the ground state of the excited state is given by this, which I think we explained in class like 2 weeks ago using very some trigonometric functions. So the probability of giving of the atom being in the excited state and the ground state is given by this sign. So I also considered I also considered another state in which the initial condition has 0 photons. That means the system was in a vacuum. And we also noticed that the same pattern, and the atom was in the excited state. We also noticed that the same pattern was observed for the probability distribution of the atom in the two-level system. There was also this sinusoidal oscillation of the system in the two-level system. And it could, when we talked about the light and matter interaction in the semi-classical way, this is not possible because there was no E, the field E is 0. It tells us that the atom will always remain in its excited state and not come down and would not move. But because here we are considering the interaction of light and matter quantumly, and it shows that despite that there is no photon in the system, we still observe that the Rabi frequency has a 2G, and it is moving as seen, as observed in the previous slide where your photon was available. So, and this was as a result of the excited state having an extra reabsorbing and emitting the same photon in which it's used to excite initially. Okay, next slide. So we would have concluded that the situation I described before was situation in a non-coherent state. We would have considered that this situation will be similar in a coherent state. And coherent state was described by Hadassah in our previous presentation, where she described what a coherent state is. We noticed that our oscillation, the Rabi oscillations, the frequency, the movement of the atom between the excited and the ground states it's not periodic and regular as seen in the previous slide. And we asked why. So let's consider a more general solutions of the dynamics. So I considered a wave function for the atom, which is this at time 0 and this is this. So the solution of the equation for the Schrodinger equation was given as this. I didn't solve it. I didn't confirm. I'm a very trusting person. I believe them. So, and we explore the scenario in which the atom is in the excited state, whereby the coefficient is 1, and the coefficient of the excited state is 1, and the coefficient of the ground state is 0. And we came to this conclusion. I did this, it was a bit easier, so I confirmed this. So, and we got this. So when we got this, and the atomic inversion also, which also describes the probability difference between the excited states and the ground states, which just gives us the information of how the amplitudes, the atom moves from the ground state to the excited state, gives us this. So to visualize this, next slide. To visualize this, this gives us the rise. This atomic equation gives us this kind of reviving and collapsing of an amplitude in a two-level system. And this is actually very different from what we observed in a non-coherent state, and also the semi-classical and quantum states for the non-coherent states. So this is actually very interesting, but this is actually very fishy. So this is a plot of the atomic inversion, which also shows the probability distribution between the difference between the excited states and the ground states. This is actually funny because based on the recent research I'm doing, the amplitude doesn't return back to its original position. It gives small, like this, like it collapses and never returns back to its original amplitude. But this one is going back to its original amplitude. I might be wrong, but I just observed that this is quite funny. So this, we notice that the periodic and regular oscillation noticed in the non-coherent states, given by the semi-classical and quantum states, is lost in this coherent state and gives rise to something that looks like my mood most days, something like this. and I think David will be explaining to us what causes this, because I'm actually curious to know what causes this. Thank you.
Mistaken. Do not believe there are witches.
Yes.
On slide 3.
This one.
Yes. In your first equation, the Hamiltonian interaction, Hamiltonian equation, below the A and the E, you have dots. What do those dots represent?
It doesn't represent it. That was the simplest representation of the animation that I saw. So I just went with it. It does it. It's an free animation, and I was trying to give you the animation and the rising and lowering operator of atoms in the field.
Okay, what do the dots indicate?
It was just thinking as an operator. I don't think it represents anything.
So they're just a typo?
It was intentional, but the A was supposed to be an operator. I just stood for this is well, yeah. A is just an operator. I didn't think too much about it, so I was trying to
So by removing this dots, nothing will be lost. Okay. Please verbalize, because it is important for all of us, maybe later. How does frequency of radio oscillations for number state, for initial state with fixed number of photons, how the radio frequency of oscillations depend on number of quantum?
This rabbi frequency is gotten from GT and this whole thing, no, G and +1. This whole thing represents the rabbi frequency.
Please say by simple words. If you have more quantum, would it be oscillating quicker or slower?
It's very
Oscillates quicker or slower?
we hope.
Okay, so larger number of quanta gives quicker oscillations.
Oscillations, yes.
Okay, yeah, thank you. And one more question that no one of us prepared, but if instead of field in coherent state, one would prepare field in the thermal equilibrium, like black body state, what would be the dynamics? Can you guess?
Dynamics was similar.
Or it would be without oscillations, just directly going to zero and then stopping. I don't know too. It's something interesting to check. Did you got the question? Right now, Patricia assumed that the field is in the coherent state that was introduced by Hadassah. But one can also prepare field in the thermal state where a number of quanta follows just Boltzmann distribution or Bose distribution. What would be the effect if you take Jaynes-Cummings model and prepare field in a black body thermal state? We can challenge David with the same question. More questions to Patricia? Questions one? She's real. Already identified himself. So you want to prepare
Yes. Then I don't know if you can just do like a page fit thing or something.
scrolling. Oh, yeah. Ancient world. Manuscripts.
Yes. Oh, okay, well, that's going to work. Yeah, so I'm going to be presenting the Heisenberg operator method for the Jaynes-Cummings model using like the ladder operators, which I'm kind of using as a general term. So basically, we're looking at like a perturbation theory type thing, right? So our unperturbed Hamiltonian is our like non-interacting photonic Hamiltonian, our non-interacting like two-level atom, and then we have the interaction part here, which is this is the same Hamiltonian as we've seen in the last couple of slides. So this V is our photon frequency. Omega is for the electron in the atom. A dagger is a photon creation operator, photon annihilation. Sigma Z, I guess I don't really know how to describe that well, but basically these sigmas are ladder operators between the electronic states, and the A's are ladder operators between the photonic states. So we've got the Heisenberg equation of motion here. So we can use that with all of our, ladder operators, right? So we can write this thing down like this. And I tried to actually, write it all out and convince myself that this is actually the correct final answer. I'm pretty sure I did this stuff wrong though. Well, I mean, this one will be fine actually, but like in this case, I guess I'm not really 100% sure, because if we had like 10 photons, doing 2 annihilation operators, it'd just bring you down to 8, right?
We do not, before thinking, one needs to make sure that everything, notation follows Wick's theorem, as Hadassah taught us.
Yeah.
And then it will clarify itself.
Yeah. I mean, it works if I did it this way, but when I woke up this morning, I realized that that's questionable at best. But anyway, yeah, so like the time derivative of our like photon annihilation operator gives us this expression. And then we can
Which is linear in other 2 operators, right?
Correct. Yes. Yeah, they all turn out that way. We can do the same thing for like the lowering operator between electronic states. You go through the math. These ones I am actually more sure about. Like that is for sure 0, right? Like these 2 do simplify to a negative sigma minus. So these ones are good. But we wind up getting a nice linear expression again, kind of.
Oh, it's non-linear. You have a product of operators as Z times A.
Oh, yeah, I suppose. Yeah. That's what we do.
It's still doable, but it is a
Yeah.
little problem.
But they're for different things, so it's not so bad. And then we can do the same thing with the final operator that we haven't looked at yet. The sigma Z one, follow through. All these ones should be good again. And then we wind up getting an expression that looks like that. And this G is just a coupling constant. I don't think that I actually labeled that on the slide where I introduced all this stuff. But it's like the dipole moment. I don't know. It's a constant. So then we can define a couple of constants of motion in the form of like operators. We have the total excitation operator, which basically tells us, you know, is our electron in the excited or ground state, and then like how many photons do we have. And then we have the exchange constant, which I don't really know how to describe that, I guess. And we've got it in terms of this delta, which is, that's just the offset parameter that we have in all of our codes. It's just how far off are the photon frequency and the electron like level frequency. And both of these things commute with the Hamiltonian, which is nice.
And then the expectation, the contrived plan is if one ever needs to take time derivative of those, they will be zero, and it will simplify next steps.
Yes. So we're trying to ultimately solve for like, you know, sigma minus of t or like a of t. So if we take this expression that we have for sigma dot that we got before, we can just take a derivative of this, you expand it out, we get this derivative and this derivative, but we have expressions for those, you plug it all in, you get this thing. And then, okay, so this is what we're looking at now. So we can rewrite this term as this, again, in terms of like a sigma minus dot, but that's actually a good thing. And then we can also rewrite, I think, yeah, this one as something a little simpler.
So using
What now?
using constants of motion, one can fight the nonlinearity,
Yes.
right? So
Yes.
instead of combined product of three operators in a sequence, one has just a constant of motion times operator.
Yes.
Which is
Yeah, makes life a little easier. Yeah, so then we just rewrite that other one like this. And so basically that gives us, you know, sigma double dot plus sigma dot times some stuff plus sigma times some stuff equals 0. So if we keep going down, so that all that stuff allows us to recast that equation like this, where we've got everything in terms of just multiple different derivatives of sigma minus.
well, this equation is linear, right? In operator sigma minus.
Yes.
So nothing, everything else are constants.
Right. So this is a differential equation that's reasonably easy to solve. And then we can get basically the same expression for A operator if we do that. I haven't actually done this myself, but I'm assuming that based on your feedback that you gave, that if we just subtract these things, we've got the same coefficients in front of everything. So then we can solve for sigma double dot, or sorry, for sigma minus A, this thing. And then we can also solve for the plus, and then that will end up giving us our final expressions for sigma minus, which we can relate to sigma plus pretty easily, and for A of t. So they wind up looking like these. These kappas are just constants, which are defined on the next slide. Yeah, this is just what kappa is. And then these things supposedly get used in solving for that. I don't know. I didn't have time to actually go through it and do it myself. But yeah, so basically we got the time-dependent ladder operators, which is what we were after. And those things are useful to solve for multi-time correlation functions in the Heisenberg picture. And there's just like a couple of examples on the next few slides. So we can solve for like the population inversion, where this is a combined state. I'm just using like 1 and 2 as like the electronic ground and excited state. And then this is a coherent photonic state, like we were just talking about. But yeah, we just get a nice closed form solution for it. And then we can also do like dipole-dipole correlation functions, which looks kind of gross, but it simplifies pretty nicely under the right approximations. Not really approximations, just like initial conditions. So if we're in resonance, this delta is 0. So like that goes away, right? This whole term goes away, that thing goes away. You can simplify these things greatly if you're looking at specific examples. Yeah.
So what's the space if we have tau equals 0 and delta equals 0?
If tau equals 0 and delta equals 0.
The same way as previous speakers
I believe so, because this just turns into 1, this whole term goes away, so we're just left with this guy. This is 0, so it's just omega squared. Tau is 0, so this is just 1. Same thing here, that's 1, this goes away, so that's just omega squared again. And then this thing would survive. Well, it'd be a function of time anyway, but it'd be a more simple cosine function.
So sigma plus sigma minus is population, right? Of two-level system, not inversion, but just population.
Yes.
Same collapses and revivals as Patricia has introduced, and David will discuss later. But it would be really interesting to see the result of the Heisenberg method and expansion coefficients method coincide.
They should under the right conditions. Yeah, that's pretty much it. I didn't really know what other conclusions to draw other than that the Heisenberg method of doing the ladder operators is useful for multi-time correlation functions.
Okay. Please join me in thanking Landon. Any questions? Adam, any comments? I already expressed my questions, so let's count down. If anyone remembers the question, go ahead. Questions 1, questions 2, questions 3.5, questions 7. And I think we did about half of the talks in an hour. So David is going to summarize the key findings of the previous papers.
So I am looking specifically at the collapse and revival that was briefly talked about by Patricia. So here we have our initial state, which is the coherent state that Hadassah talked about, and it's actually one of the equations she gave. And then if we use the time evolution operator on it, you end up with this fun equation. And then what we are interested in is the probability of flipping into the excited state, which is given by this equation down here, where we have this mean photon number, which is, you can think of as how many photons there are. So then if we then work with our probability function and we take based on the Poisson distribution that again Hadassah talked about, we can come up with this equation. And then if we expand this omega n around this point, we get this. And then if we plug this into this, we get this equation out, which is a complicated exponential within exponential equation. So what we do to make this simpler is we consider small times such that this delta, not delta, omega t/2 is much less than the square root of the mean photon count. And when we factor that in, we get this out. So what we see is that it's going to oscillate around the effective frequency. So what you get this oscillation. And what we see is that it decays, and this is, you can think of it as a destructive interference between different frequencies. So it decays here, but as time goes on, we start to see an increase, a revival of the probability, and that can be due to the rephasing of the frequencies, causing increase at later times. And Patricia actually showed one that goes even farther along than this one. This one just shows the initial revival. So this has been actually demonstrated experimentally. So this is the experimental setup where you have your cavity and then you have your oven to create your excited atoms, and they select for velocity. Yes, velocity. And what we see if we look at the results, so we have two of these oscillating spectra. So here you see that it continues a nice oscillation. This is with a low mean photon count, where this one has the highest mean photon count they could get. And you see in here, we do see this collapse and then a revival again as they go along in time. So what they do see the revival and the collapse when they start getting higher photon counts, and it's like I want to say a 1.7 mean photon count. I think it was 1.7 or 1.77. That's all I have.
Okay, please join me. Thank you, David. Any questions? So we have a lot of experts in Jaynes-Cummings model in the class, so questions will be not unexpected to someone. Same, let me ask you to comment on the same question that was asked to Patricia. What if it is a thermal state related to your talk in the previous session? If the photon cavity mode is in the same state as black body radiation, what would be the expected trajectory of the atomic populations?
If it was black body, I would expect that it would, and this is, I have no idea if this is true. I would expect that you would see a more consistent, less oscillatory pattern somewhere, depending on the actual thermal equilibrium based on Boltzmann's rules, where it would determine where exactly it is. But I would expect a much more consistent pattern that in this.
And when would be the intuitive arguments to expect that there will be no oscillations at all? It would just slowly damp to the 0.5.
That yes, I would imagine that that you would lose the oscillatory nature.
Mm-hmm.
Why?
Because the thermal population doesn't have maximum. It has less and less as we go from 0 to higher, and the destructive interference is expected to dominate. But I do not know it for sure. I didn't do this experiment and didn't read it. So I'm on the same boat as you. So it would be really interesting to either read or derive. More questions, David?
I want to understand what is causing the revival and the collapse. Like what I'm asking is like, can you point to the equation?
Back, like
The equation that, oh, this is something that is different from what we have in our semi-classical and quantum in a non-coherent state that is present in our coherent states that is causing the collapse and the revival of our population.
so we are we have this cosine value right here, where this omega is the Rabi frequency, or yeah, or something at least analogous to it. But we can have several of them. So what you get is you get a range of these that are causing causing interference. So the reason you get this initial collapse is it's causing destructive interference. But as time goes on, they're starting to come back into phase or dephase, or I'm not entirely sure which is the correct term there. So they start coming back together and you get an increase. At least that's the way I understand it.
The Rabi frequency oscillates the time. Does it?
It's because you have slightly different frequencies.
Okay.
So we don't have the same frequency in the coherent state.
What do you mean?
Say, I don't know. When answering the question, you said we don't have the same frequency
We have several frequencies.
in the coherent state. Oh. Okay. How is it possible?
Patricia, you did answer this question. So for number state, Rabi frequency does depend on number of quanta, right? Then going back to atom, there are block diagonals. So in each block, in each pair of eigenstates, there are Rabi oscillations of its own frequencies. And when they are occurring simultaneously, it's same as in our lab last night. So oscillations with different frequencies come together when find superposition, and when they are sufficiently off phase, they cancel each other. But when they keep accumulating phase, after some time, they will come back to the phase. So it is because in Adam's talk, there are block diagonal form of the Hamiltonian, and because you who told that Rabi oscillations depend on number of quanta. David, would you?
Yes, that's a much nicer way of saying what I just said.
Yeah, go ahead.
No,
Last chance for the questions. 1, 2, 3. Let's thank David once again. So we have 29 minutes for more talks, but David was completing the subject of atom in a cavity. From now on, we have we shift the gear and do a little bit different objects. Focus.
All right, so I'll be talking today a little bit about double-sided Feynman diagrams. So we can. All right, so I wasn't exactly sure when I picked this topic what exactly they were, so I just want to go over real quick of what they actually look like. So this is what a double-sided Feynman diagram actually looks like, where each of these blue lines is ket and bra respectively. And then the time evolution goes upwards the farther up you go. So these can be pretty much as long as you want, depending on how many steps you have in your system. This one is just a very generic one-step one. And then these lines show the different times. So this bottom one would be like your starting material at ground state. And then at a specific time, which is indicated by the dotted lines, it'll then switch into this state, and then so on and so on. So if you would go on to the next one, I talk about a little bit more of what's actually inside. So part of my talk, I was supposed to talk about what is the connection with the density operator for these. Well, actually, the density operator is this part in the inside. So using the Louisville equation, which is up in the corner, we get our density matrix in row, just given here. And using that density matrix, if you just tap one more time, another photo will pop up. Yeah.
You're correct.
If you tap the screen one more time, it would just bring up a photo. There it goes. Okay, so this figure is actually for this density matrix for 2x2 that is commonly known for a 2-level system. So from my understanding is that these 4 figures all show the same thing, but slightly different. Because with the figure itself, we aren't sure exactly how absorption, which is the arrow going into, and then emission, which is the arrows going away, actually interact yet. So this is us saying that, well, these are the most possible ways. And that it could possibly be, but we're not so sure. That's what experimental is for, is to see which of the diagrams actually work. From my understanding, it seems to, for the majority, be a mixture of all 4, which I thought was interesting. If we go to the next slide, this is the old slide. Okay, so on my new version, I did include another slide in here that kind of talks about more of what the diagrams actually mean. I can use this slide to get to it. Yes. Good. Okay. So from these diagrams, we can get something called a correlation function, which I'll talk about more when I get back into the 2-step systems. But so we have our diagram. Okay, that's up here. So we came up with this diagram, but what it could potentially be, this one is a super simplified version just for simplicity and trying to get thoughts across. So the system is taken to start in the ground state, and then the linear response only allows for one input field, which is given here. In this case, the input field always starts on the ket side, is from what I can see. So it's always absorbance that is acted on the ket over the bra. Then with the diagram, we can begin by describing the signal characteristics in terms of the induced polarization, which I give here. This is just bringing us back to that, I want to say Louisville, that's not the word, but that, yeah, it is Louisville. So the Louisville type of equation where W sig is the same as W1, and then K sig is the same as K1. This is just bringing us back into terms where we are using rho instead of energy. So we put it into that, and then we take the parts of actually in the figure to actually get us that correlation function that uses this. So first we take the ground state, which in case for this one, it is rho AA, but for simplicity, they just wrote it as PA, probably just to save them from typing a couple more things. So that gives you the first part of the function. Then you go to the first dotted line, which is where the absorbance acts on the ket. And that creates our row of, in this case, BA. So that gives us, because we're acting on the what's the name? Mu gets added there in the BA state because the absorption is acting on the ket with mu. So then you go for the space in between, which is the time that it propagates under the initial Hamiltonian, giving us this equation here. This is the same equation because if you have multiple steps, you have part 3 for multiple times. And it seems that equation is the same except for tau changes from in this case, this would be tau 1, and then you'll have tau 2, tau 3, tau 4, and so on like that. So propagate under the initial Hamiltonian to get you that equation, which you then put right after the second part. And then the fourth part is where you get your trace from the ket, then doing the emission. So the emission is acting on the ket again, based on mu, which is why we get mu AB, because it's just the inverse of step 3. So then, because it's just the inverse, from what I see, I'm not exactly sure why they put them together, because to me they're two separate things. But whenever you have the same thing, but it's just the inverse of the other, they still put it together as the first one, and they just square it. I'm not exactly sure why. No one really explained it. But this upside down LBA actually refers to the dephasing rate of the coherence of, in this case, it would be rho BA, which equals to 1 over T2, which I believe is tau 2, which does correlate to something that Stephen will be talking about in his next, in his presentation. So we can go on to the next one to see if this actually used more in an example. So in a photon effect, you pretty much, photon effect, you can have it in a two-step system, as I am showing here. Again, these are just showing all the possible ones, and this is showing our not coherence, correlation function of R2 is obtained by using the same thing that I just showed for this, and then we also show it for R4. I show it for both because the only difference between the two is this, what would be the third step from the previous slide. So for R2, it goes from A ket, which is our ground state, to B, or for R4, it goes from B to A. So for my understanding, this difference changes the sign for the phase that is acquired through tau 1 and tau 3 as shown here. So pretty much for R2, it's a minus sign, instead of plus sign. And this upside down L with a BB for rho of the excited state actually is the relaxation. Yes, is known for, it's the relaxation state instead of the I'm sorry, I'm blanking on words today. Instead of the dephasing state like was originally seen with the LBA. So this slight difference between the R2 version and the R4 version is actually due to rephasing. So R2 actually has the property of time reversal. So the phase acquired during the T1, which is here, is reversed in T3 because we go from A to B to B to A. Unlike in forwards, we just stay with the ABA. Because it switches from tau 1 to tau 3, this is actually called rephasing. The rephasing signals are selected in photon echo experiments and are used in distinguishing line broadening mechanisms and study of spectral diffusion. So that's how these diagrams can be used in photo echo and actually seeing where the photo echo will actually happen in your experiments. And then if we move on to the next slide, it's a little bit about the spin echo. Now I did have a little bit of issue actually finding some figures for this, so I apologize for there not being figures. The spin echo is a technique that is used in MRI to reduce the effects of inhomogeneous in the magnetic field. So it works by applying a second radio frequency pulse to a fixed time delay. So you'll have your first pulse, and then after a certain amount of time, another pulse will occur. So this actually has it. So it actually fixes the the Inhomo word. I'm just gonna call it Inhomo from now on because I cannot pronounce it. But it actually fixes it for your sample, so it will actually, the cyclic pulse will rotate everything by 180 degrees and will make it so you have a stronger signal. But these Inhomos causes dephasing of the spins, which is where the diagrams actually come in. So again, you can actually see where the dephasing will occur depending on if the broadcast actually switches when you get from a certain tau to another tau. So from my understanding, so the spin echo is through the interactions done on the diagram. And this leads to changes in the rotation rates of the spins, which can affect the efficiency of the spin echo pulse sequence. And that these effects all do depend on the experimental parameters of the MRI system. So from what I could tell, it's all based on the type of MRI system you have. So I know there's a whole bunch of different MRI machines, so I think it varies between each one, and why. I think that's the main issue why I had issues finding actual images to show you guys for this. That's all I have. Are there any questions?
Great question, thank you. Tori? Yes.
So I missed the beginning of your talk, so I might have just missed this. The straight arrows are absorption and the squiggly arrows are emission.
If it's pointed towards the Broadcast, it is absorption. If it's pointed away, it is emission.
Okay, so what's the difference between the straight and the squiggly lines?
The squiggly lines is your end thing, so it's the, I'm blanking on the word.
Just radiated and continuous.
Yeah, so straight, I'm pretty sure is induced, and then the squiggly is your spontaneous when it's done.
So in our lab last night, code number 4, we did send in 2 pulses that were inducing transitions, and then we observed that there is a rephasing. We didn't compute it literally, but it is very much expected that if everything phases, a spontaneous emission will happen. And I believe what Tori denotes by this wiggly line, it means when system comes into phasing, it will spontaneously emit avalanche of quanta with a certain frequency in a certain direction.
Okay.
All the figures that I've seen, it seems to mainly be done on the cat side.
Yeah, that's what it looks like. Yeah. I don't know, I have to think about that more.
I'm having trouble understanding the dashed line versus the solid line. You have some, I guess, dashed lines for the arrows that are on the right. And then the solid refers to the ones on the left. Your Feynman diagram. Does that make sense?
No,
Yeah.
talk about these ones.
Yeah.
Oh, okay. So if they're solid, then it's only affecting the cat side. If it's showing the dash, then it's affecting on the bra. Or at least that's how they're showing in this figure, just to show the difference between the two. So this one is the first one that comes up, and because we start at the bottom, coming from the bra side, so that's why it is dotted up. And then absorption is also coming from the cat side, which is why it's showing solid. And then emissions going off on the bra. Does that help clarify or answer your question?
I'm just having trouble conceptualizing.
It did take me a while to understand these figures. If you want, I can try to help walk you through it after class.
Okay.
Suppose we do not believe in density metrics, but we still believe in wave function. And I'm not going to say something right. It's only like navigate the direction of thought. Suppose we have 2 streams of events. We have not one particle, not one 2-level system, but 2. But one of them is moving forwards in time, another moving opposite, backwards in time. Right? So one has positive frequency, another has negative frequency. Okay, so they two coincide, and then we can selectively irradiate either forward going or backward going system. Can you imagine this?
Yeah.
Okay, now we agree on this, we imagine this, then we tell next density matrix is when forward going and backward going is the same system, but in bra and cat form. Therefore, the same system can be irradiated either from left or from the right of this diagram, which means it affects forward going part or backwards going part of the system. Okay.
Okay, yeah.
It's more like back to the future. Fluctuator fluctuates. More questions to Tori? Yes.
I think for like photon echo and spin echo, are they like different concepts or they're in any way like related?
So from what I can tell is they're somewhat related, but they're not explicit. I think the spin echo itself, and I believe Stephen will go much more into detail on both of these, but the spin only focus on like the half spin. So while the photon focus on just the photon itself, not necessarily the spin of the photon.
The discussion. So mathematically, it's very hard to find differences. Both, if you speak about spin echo for doublet and photon echo for only two level systems, then most of the math, or even all math, is the same. So they just happen in different frequency ranges. So the photon echo happens at like femtosecond domain of oscillation period of electromagnetic radiation, and the spin echo for radio frequency, which will be like between microseconds and nanoseconds. But the same quantum effects of dephasing and rephasing are the same. They just happen several orders of magnitude quicker or slower. There is one thing that is observed in photon echo, but is not observed in spin echo. So for photon echo, there is also dependence on momentum in spatial direction. So if your radiation is sent by lasers with very selected momentum vector, okay, first laser, second, then the resulting emission will happen not randomly everywhere, but also in a certain direction. And it is a little additional piece of math to predict it. So one can take a sample, irradiate them by optical pulses in one or another direction, and then it will shine like a little laser in a certain direction, face selected orientation. Okay. More questions to Tori? Questions 1, questions 2, questions 3. Let's thank Tori once again. Thank you for being so brave and covering a very advanced, complicated subject. So we do have 3 talks for 28 minutes. Be explaining. Yeah. Stephen is admitted to the club of advanced theorists who do not fear to come to the board and write equations.
So today I'll be talking about multi-pulse NMR spectroscopy, which is pretty sure almost all of spectroscopy involving NMR. In particular, it's style used for medical NMR, also known as MRI. The word nuclear is scary to people. And also its connection between inhomogeneous broadening and the spin echo phenomenon. So first, a few basics of NMR. While only a few elements are capable of becoming permanent magnets, most notably, I think that all of them are central transition elements, central transition metal elements. Many more are capable of being magnetized when in an existing magnetic field. In particular, it's all elemental isotopes that have a spin of 1/2. So because these are only held into an alignment by an external field, they're pulled out of their resting state position, either in line or against the direction of the magnetic field. Several interesting things happen. Slide. So the first of which is called inhomogeneous broadening, and it's related to what I'll be talking about after this. So in an ideal system, all of these elements would decay from being when the magnetic field is released and they're allowed to fall back to their resting position. In an ideal system, all of the elements in a single sort of model system, like say a group of hydrogen gases, would decay back to their natural resting state at the same weight. However, the world is not an ideal place, and it's very important that it is not. So at the atomic scale, imperceptible fluctuations in the chemical environment disturb the relaxation rate of each one. Even though it's a pure sample of one element, ever so slight vibrations in, say, atomic bond distance or some other secondary effects of a non-interacting system next to it or its position relative to the magnet. So these, you might assume that these are random, and for trying to mathematically describe them in a way that is understandable by a human, they might as well be random because a single atomic scale. It's far too small. However, they are not actually truly random, since they are affected by the position relative to some fairly constant things, talking at the scale that we're working at. So this is also known as spin-spin relaxation, since it's involving purely the interaction of spins. And importantly, it is defined by the time t sub 2, which is defined as the time it takes to reach 1/e, Euler's number, which is roughly 37%. And that would be this top equation I have here. So assuming that we have elements being pulled into the XY plane from the resting state in the Z direction, the time it takes for relaxation, so mxyt, is mxy at 0 times Euler's number negative time over T2. T2, of course, being a material specific constant for each unique element. I believe Tori mentioned this a bit sort of in when we have medical imaging, the different chemical environments of each of our body tissues produce different T2s and T1s, and this is what allows us to get distinct images that we can resolve out of MRI. Next slide. And so what does that have to do with spin echo? So when you have a series of pulses applied, in particular, you have what's called a pi over 1/2 pulse, or a 90-degree pulse. This is pulling it from Z into the XY. It's a 90-degree turn. And then you have some length of time. I'll just note these T1s, T2s, T3s, T4s are not related to my capital T1s and T2s. That would be the ones on the bottom. You have some length of time between that and what's called a 180-degree pulse, so a pi pulse. And there's some more math that I could go into, but I don't want to because it's multiple pages. So something very strange happens. So we have our sort of disruption from our Z direction into our XY plane, and then this resolves as they relax back into the Z direction in sort of that spiraling reverse top sort of motion that we've seen in class. I couldn't find a good picture of that to use. And then after we have apply our pi pulse, something very strange happens in that roughly at time t between the pulses, we see a signal echo appear, where it rises into the same energy or nearly the same energy due to, again, minute fluctuations in energies at roughly the same rate that it decayed at, and then it decays again. How can that happen? And I had something to say here, but I kind of forgot it now. But importantly, so as we, and this is what T1 comes into. So we're pulling our spins out of the z direction into the xy plane. And as they're processing around in the excited state and returning back to their z direction, they do so at different rates as the inhomogeneous broadening. They're spreading out at different speeds, even though they're this, in theory, entirely identical. And I think yes, I'll just explain what on this. So starting with our Professor Killian's wonderful race example, we have our excitation, the starter gun goes off, and our runners, even though they are all excellent athletes, they proceed around the track at different speeds. When the starter gun is sounded again and they return at their own independent speeds and arriving at the starting line at the same time again. So here we have our excitation and it's pulled into the XY plane and they spread across, and then we have our 180-degree pulse, and now they spin across the block sphere that we see here, and they return and they reconverge on the other side and form the same, I'm blanking on the word here, convergence, I already said that. They come back together, re-enter phase and produce a signal like we saw before they began to diverge due to the broadening. And so one last thing. So how does T1 and T2 exactly relate? Because I already told you that T2 is basically the time that it takes for the signal strength to decay to 37% of its peak. Well, T1 is what it takes for it to reach, and I also said that 1 over E is roughly 37%. T1 is how long it takes for the return to the Z direction to reach 63%. You might say, Stephen, you have an exponential decay in the time that it takes to reach 37%, and then another exponential decay of the same numbers in the time that it takes to reach 63%. That's the same thing described in different ways, and you would be entirely correct. Because what we were measuring when we have our excitation, an exponential decay to 0, and our reconvergence of phase to Z, they intersect at the point that one is 37% and one is 63%. And to be honest, I feel like I'm forgetting something I meant to talk about, but I can't remember what it is. If I didn't, obviously I would talk about it. But that is my last slide. Does anyone have any questions?
So your T1 and T2, those are the same T1 and T2 that we were talking about in lecture, like 1 or 2 lectures ago, right?
Yes.
Okay. I just wanted to make sure that I'm understanding that correctly.
Yeah, I just want to confirm that the way an echo is being formed is when, this is a clarification, is when a pulse is being introduced to a system with different pulse area. Is that how an echo is being formed?
Yes, that sounds right.
So if the pulse area is the same thing, if different pulse area is being introduced to a system, an echo will form.
Can we go back one slide or two? Yes, Jay. So you're saying, so we have a pi over 1/2 pulse here, and we have a pi pulse here. So you're asking, if instead of having a pi pulse, we have another pi 1/2 pulse, we would not see an echo? Yes. And if we go back to the next slide now, this is the key point. So we have that was our 90-degree pulse pulling it into the XY plane. That 180-degree pulse, the pi pulse, is crucially what takes it from being diverging around the sphere at different rates to having them sort of flip direction in place and start converging again. And that are, yes. And so this is our T1 decay that it's showing here on the top. is the time that it takes for the signal echo to decay. So yeah, our echo is the point at which I probably shouldn't clap for that point where they flip, and they are now, even though they haven't really changed which way they're moving, they've changed in relation to each other, and so now they're moving closer together and back into phase.
Just one more question out of curiosity. What we described in the lab yesterday was also pi over 2 and pi. What's at the area of the pulse changes? Like they are also different like changes. Would an echo still form instead of the 19, the regular 19,
I'm not sure, and unfortunately, I missed lab last night and have not had time to watch the video recording yet.
Repeat the question.
What she asked is,
in the lab last class, we also talked about pi over 2 and pi as the area of the pulse. Now, what if we confirmed that a pulse is being, an echo is being formed if the area under the pulse is different? So what if the area under the pulse is not the regular pi over 2 and pi?
Okay, the signal will be messy. It will not reface so nicely. And it will be quite sensitive. If you do not tune area of pulse to this pi over 2, they will not reface so nicely. And you can do it with the code, just modifying this denominator variable, and you see that it will generate just a big mess.
working with our runner example, it'd be like if we had one of them start off just a second earlier, and then another one a second later, another one a second later, and had them all offset by 1 second, moving at their own independent rates, and then had them return. They wouldn't all return back to the starting line at the same rate, even like they would if they started all together. They would return 1 second, and 1 second, 1 second, 1 second.
More questions? One?
Oh, it's spectroscopy.
Yes.
Hoping I can get an answer to this because I've been wondering this for a really long time. What's measured? Is it just is it the echo? Because you get a plot and you get certain peaks on that plot, different ppms, that represent certain frequencies. So what is measured here?
That depends on the exact nature of how you're measuring it, because you can measure both of them. In fact, the determination of what T2 is done entirely by conducting this 90 and 180 degree pulse, and then measuring the formation of the echo. So it's how you determine T2. Fun fact, if you look at the Wikipedia pages for this, they have the T1 and T2 times for a bunch of human tissues. Yeah, because that's how MRI works.
Yeah. So in NMR spectroscopy, like proton NMR, would that be
in proton, like, so in a proton NMR, in a chemical NMR rather than an MRI, to be perfectly honest, I'm not entirely certain. But I believe they don't tune it specifically for this 90-180 pulse technology. There are some that do, specifically when they're trying to measure certain properties, but just trying to see like the chemical environment, like we're seeing like a triplet for like a methyl group. I don't think that's tuned properly to be seeing the echo. I think that's measuring something else. But again, if you want to come over to my desk right next to you and like try and figure this out later, I'd love to, because that is a very good question, but I'm not certain. We're running out of time. Yes.
Let's thank Stephen once again. We have 12 minutes to talk, so probably there will be no questions. Questions will go in the same way as Stephen suggested, through approaching desks of each other and sending emails. And those talks may induce even more questions. They're really interesting.
Okay, so today I'm going to be talking about quantum computing, basic theory, and some current implementations. Next slide, please. So first, we need to understand the difference between classical computing and quantum computing. In both, we have some kind of storage of data. With classical, we have bits, and with quantum computing, we have qubits. So in classical, we would have a bit would just be a store of an electric charge, whether it's there or not would be 1 or 0. You can think of it like Morse code, whether there's a sound or nothing at all. With qubits, it can be 1, 0, or a probability of being either of them. So it's kind of a distribution. A nice diagram is using the block sphere. So you can have it either have it at one of the poles, or it can be some arrow pointing to a value in between. What's really nice about this is how they scale in terms of how much information you can store based on the amount of qubits. So with traditional classical bits, it scales by n squared. And with qubits, it's 2 to the n. So it very quickly outpaces regular bits and how much information they can store. And a quick demonstration is, let's say we have our wave function, and it's a superposition of 1 and 0s. And as we add more, they become a tensor product, and it increases until you get 8 just with 3 qubits. And that's where the qubits start to diverge and take over. One of some drawbacks of qubits is that since they're in a superposition, we know our superpositions are a lot more fragile. So they're very susceptible to noise, whether electromagnetic, thermal, impurities. A lot of things can disrupt our superposition. And that causes a lot of errors, which I'll talk about correcting errors later on. And since our superposition and entanglement is rather fragile, we have what's called coherence time, which is how long it can maintain entanglement or a superposition. And that varies depending on the implementation. So to manipulate our bits or qubits, we use logic gates. And classically, we have logic gates. They'll take electrical signals and output a predictable electrical signal. So like NAND gates, exclusive OR gates, NOT gates, all very traditional stuff. Quantum gates, it's more like you perform an operation on your qubits through light or whatever manipulating media you use. And they're described as rotation and entangling gates. Rotation also called phase gates. And then we have what's called unitary gates, which is just a description of these different gates where their complex conjugate is equal to just the inverse of the original operator. So first, rotation gates, also called phase gates, they just impose some kind of phase change. So IonQ is a big quantum computing company, and they have a gate called the GPI gate, which just does a phase change. And it uses Rabi oscillations induced by 2 photon Raman excitation. So you just hit your ion with a photon, and it rotates it. A very generic description of this is just we have an operator acting on a system, and it imparts a phase change. Again, block sphere is a great way to think about this. Another very important and critical gate is called the Hadamard gate, which will turn a pure state into a balanced superposition of 1 and 0, where they both have an equal probability of existing. Next slide, please. And I mentioned entangling gates, which is very critical. So you can build up a large register of however many qubits you need. You have to build it. So the quintessential qubit entangling gate is called the C0 gate, which follows this matrix, which has a bit of a complex derivation to get to how you get there. But the main thing is you have a control and a target. The control is not going to change to the C0 gate, but the target will change if the control is 1. So if A is 1, B will flip no matter what it is. We also have the Molmar-Sorensen gate, which uses light-induced vibrations, and based on the vibrations interact based on the state of the photons or the ions. And so if the vibration is dependent on the other one and the other one's in a superposition, then they become entangled because you have to know the state of the other to know the state of the one you're looking at. And so it has this nice anti-diagonal. And a C0 gate can be made of one of these MS gates and then just some phase gates to get the proper rotation. And since we're talking about gates, and I mentioned errors earlier, there's also gate fidelity, which is just how often you're going to get the correct operation or the correct result from your operation, which is usually at least 99%. And I mean, below that's probably unacceptable. Next slide, please. So I mentioned decoherence, which is just whenever unentanglement occurs or some kind of collapse of your superposition. And so, like I said, this can happen from impurities, electromagnetic disturbances, thermal noise. There's all kinds of things that can cause it. Classically, we would have errors with voltage fluctuations. So if our electric signal, there's like a range for how far you can call a 1, whether it's like 0.7 volts to 1 volt. But how you account for that is you just store extra copies of your bits and then you compare them afterwards. But we can't store extra copies of our wave function. So what we do is we have ancillary registers, which we would just entangle to our wave function. Then we can measure the ancilla, and then that'll give us information on our wave function to adjust for. But instead of having to do a bunch of this, we really need to minimize the noise, which we do through isolation and refrigeration. Next slide, please. Oh, yeah. So a very showy quantum computer is IBM's Q-System-1, which is the one that I showed earlier, where it's a big reflective tube, which is kept in a vacuum. It's sealed from any light so that no light can disrupt it, and it's kept at 10 to 15 millikelvin. What's cool about their implementation is they use solid state superconducting qubits, which uses a Josephson junction, and it's just a superconductor, insulator, superconductor put into a circuit, and it's called an artificial atom. What's nice about this is since there's more to it, you can tune your properties a lot more easily. But it's also more susceptible to processing imperfections, whether it's impurities or lithography mistakes. And they manipulate it through microwaves. Next slide, please. And the one that I think I like better is IonQ's ion trap implementation, which they use ytterbium ions, they trap them in an electromagnetic field, and then put that in a vacuum. And they manipulate it through laser excitations. What's nice about this is since it's not in physical contact with anything, it's in a vacuum, it's hidden from light besides the laser excitation, it has longer coherence time, whereas IBM's coherence times is on the millisecond scale. This can go into seconds or even possibly minutes. What's also cool about their design is they're compartmentalized, so you can string as many qubits together as you want, and they're very easily swappable. And so everything's manipulated through laser light, and then when you're done, you just directly excite all of them, and then whatever light you get back, you can measure as your data. Some other possible implementations are just other two-level systems. So NMR, either spin up, spin down, or superposition in between. And then we have vacancies and diamonds where the electron that's in the vacancy can either be spin up, spin down, or somewhere in between. Okay.
Let's run for and our talk is special because it's everything we will be doing next 3 weeks in the past.
Okay, so I'll be speaking about trying to correlate the autocorrelation function with projecting quantum state of a large system onto small subsystem. Next slide. Okay, so I'll start first with like electronuclei coupling, which is important in the area of molecular dynamics, and it's basically the interaction between electrons and nuclei, which gives rise to the electron nuclei coupling term, which I'm showing here. So the last two terms shows the velocity of the nuclei and how the electronic motion responds to the nuclei position. This term is important when it comes to non-adiabatic molecular dynamics, and it's majorly required for photochemistry and excited state dynamics. Next slide. So I'm going to speak about the autocorrelation function because one of the things that we measure in non-adiabatic molecular dynamics is rate of transitions. And for you to be able to calculate the rate of transitions, you need the autocorrelation function. So with respect to the electron nuclei coupling term that I mentioned earlier, you get it from the autocorrelation function. Autocorrelation basically just shows how variables are related, like in the past time and the present time. So usually you measure like the overlap at different times, and then you sort of like plot it, and then the plot looks like that, which is like the autocorrelation function. Sorry, I'm not showing what the X and Y axis, but the X axis is the different times that you're measuring with respect to the overlap. So the formula I'm showing here is just velocity autocorrelation function, just kind of like understand what it is. So V naught here being at the time, like past time, while VT here is velocity at the current time. So just to hold the thoughts with autocorrelation function, just hold that thought right there. We'll get back to it. So trying to project the concept of a large system onto a small system, just because studying the subsystem is easier. Like if you have like a large system, but then you can easily study like a subsystem, and studying the subsystem kind of like makes you focus on the relevant problem at hand. So you can treat the subsystem as a system on its own, and then you treat the large system as a thermal bath, which is how the idea of open quantum system comes about, because he explains the exchange of energy between system and bath, which an example is the electron nuclei couple, where the electron is the system here and the nuclei is the bath. Next slide. So one common technique that is being used to study this system-bath interaction is the density matrix formalism. And here I'm showing the expression with the Hamiltonian and the Liouville equation. This expression here is the time evolution of density matrix. So the goal of the open quantum system is sort of like to have a reduced description of dynamics of the electronic system. Like I explained earlier with you have a subsystem and then you have a large system. So with open quantum system, you can easily just like measure the subsystem. So to go from large system to the small system is where you need the reduced density matrix, and it's basically the partial trace of full density matrix containing the system and the bath. So here I am showing the reduced density matrix for the system, and then taking the trace of the full density matrix, but for the modes of the bath. So to kind of like understand this system bath interaction, I'm showing this Hamiltonian here, where V here represents the interaction between the system and the bath. So I explicitly write out the density matrix for both the system and the bath. Here is the part that shows the interaction, and you can simply rewrite this time evolution density matrix as this expression here, where this is the total full density matrix, and this is the interaction between the system and the bath. So if you solve this expression, you can easily rewrite the full density matrix as an expression, as this expression, where and then if you expand this expression further by inserting this whole expression, you have psi t here, just insert it back into this part here, you would end up with this general solution here. So, but just to remember that we only really care about the open quantum system really just wants us to describe for the electronic system. So I'm bringing back the, sorry, this E here is environment, which could also be the same as bath. So I'm just switching between environment and thermal bath. So here I'm showing the expression for the density of the system, which is the electronic system here. And if I write the expression for this electronic system using the previous equation, we would arrive at this expression, which is basically the trace with the interaction of the system and the bath. But then we need to solve this expression. And to do this, you would use the Markov approximation. So here we're just rewriting the interaction here as tensor product of the system and the environment. The B and the B and the A here, the B is the bath and the A is the system. Sorry for switching expressions, but it's basically the same thing. This can be rewritten as this form. So now going back to what I was talking about with the autocorrelation function, this expression you are seeing here is the same thing as the one previously, but then if we include the fact that you need to bring in the autocorrelation function because you need to remember what it was like in the past with respect to what it is in the present. That was the t minus s. T is basically the present, while s is in the past. So you can easily rewrite this expression back as this, and this is what the density matrix formalism for the Markov approximation looks like.
Okay, please join me in please write down your questions if you have some. We will be speaking about this subject for about 3 weeks. Meeting is done. Many thanks for all contribution and discussions. Some of you need to go to chemistry seminar that has started 4 minutes ago. So the adjourn is announced. Thank you for online visitors. You many thanks for being here. We need to finish the session.